guess it's working, yeah. So I'd like to welcome everybody to today's presentation. Nice first warm spring day, so thanks for everybody for turning out. So normally David Hart, who is director of the Mitchell Center, is the master of ceremonies for these events, but he was called away to on some family affairs that he needed to attend to, and sends his regrets. And he was really sorry he couldn't be here to hear your talk in person, David, but we are recording it. So, so I'm Kate Beard with the School of Computing and Information Science, and also with the National Center for Geographic Information Analysis. At Maine, we have two sister centers in Santa Barbara and SUNY Buffalo. And so between the Mitchell Center and NCGIA, we're really pleased to be able to co-host today a presentation by Professor David Maidment. So he's a professor in civil engineering at the University of Texas in Austin, and it's in the Center for Research in Water Resources. He's from New Zealand originally. He got his undergraduate degree at the University of Canterbury in Christchurch, New Zealand. And then he went on to get a master's and a PhD at the University of Illinois, Urbana-Champaign. And he's done numerous things since then. And I say one of the most wonderful things about David, and there's many, is he's been this tremendous force behind linking geographic information science and hydrology. So sort of taking these two camps and really doing some serious interdisciplinary integration. And he's received numerous honors for this work. I can mention just a few. He was elected to the National Academy of Engineering in 2016, and it was specifically for this development of geographic information science applied to hydrologic processes. He was recognized as the Geospatial Scientist of the Year in 2014 for his work, again, in applying geographic information science to hydrology. In 2010, he received the Community Service Award of the Consortium of Universities for the Advancement of Hydrologic Science. This is WASHI. He's been intimately involved with that for a long time. In 2003, he was awarded the Lifetime Achievement Award from ESRI, which is one of the major vendors of geographic information software. And I could go on. He's also been a chairman of 5 National Academy committees and member of 5 National Academy, member of 5 National Academies. And just recently finishing up his chair of the Committee on Mapping Science. He's been a chairman of the Committee of FEMA Flood Maps and chairman of the Committee on Floodplain Mapping. So we are really honored to have David here. His most recent effort has been this really substantial undertaking to develop this national water model, and he's going to be describing this to you today. So would you please join me in welcoming Professor David Maidment. Thank you.
Well, thank you, and I appreciate the opportunity to be with you here today in Maine. My wife has a cousin who lives in Rockport, so I have some personal associations here with the state. And we were in Camden actually this a couple of days ago, and I realized this feels familiar to me. And after a while, I realized what it is. This feels like New Zealand, actually. The sort of socialization, certain civility of the way you treat people and so on. It hadn't occurred to me that there could be a place in America that feels like New Zealand. I live in Texas, and we can be conservative or we can be very conservative. Yeah, that's the choices we have. Anyway, I've entitled this lecture From the Magnifying Glass to the Microscope, and I want to explain as I go through why I've chosen that particular title. And I want to start with this as a point of departure. I want to ask the question, how is new knowledge discovered? So a few years ago, I edited this handbook of hydrology. It took me 4 years, and it was 58 authors and so on, and 1,400 pages, covers all fields of hydrology. And I asked myself the question at the end, how was the knowledge in this book discovered? How was it created? And I concluded that there were 3 ways: by deduction from existing knowledge, by experiment in the laboratory, and by observation from the natural environment. So I don't believe there are 23 ways that you discover new knowledge. For me, there are 3, and this is what they are. And I want to just give three examples of people that exemplify those thoughts. So this is deduction. This is the classical path of rational mechanics, and Isaac Newton was the developer of mechanics. And this is his book, The Principia. Who's got a copy of The Principia that they read? Yes, we need to get that one. It's from the University of California Press. And in the introduction he said, the ancients divided mechanics into two parts, the rational, which proceeds accurately by demonstration, and the practical. It occurs that mechanics is so distinguished from geometry that what is perfectly accurate is called geometrical, what is less so is called mechanical. Yet errors do not come from the art, but from those who practice the art. In this sense, rational mechanics will be the science of motions resulting from any forces whatsoever, the forces required to produce any motions accurately proposed and demonstrated. So that's the introduction to the Principia Mathematica, written on the 8th of May 1686, and it is the basis of modern mechanics of engineering, actually. So this very great sense of precision here that transferred from geometry to mechanics is what Newton contributed. For me, the greatest of the experimenters is Louis Pasteur. Louis Pasteur showed with microscopes. He used to carry a microscope around all the time, wherever he went. He would go to factories and he would carry his microscope. A simplified view of the natural world replicated under controlled conditions. Louis Pasteur was the first person who demonstrated that microorganisms could cause disease, and he also invented vaccination. It's a foundation of scientific medicine, actually. And so, although of course experimentation is a very important thing, it's hard to do that at the global scale. And finally, observation. So who's got the origin of the species? Now come on, somebody's got it. Oh, there you go. Okay, we've got some origin of the species people here. Okay, I'm glad to hear that. So this is my copy of the origin of the species. I keep it by my bed sometimes to read it in the evenings. So Charles Darwin said, when on board HMS Beagle as a naturalist, I was much struck with certain facts in the distribution of the inhabitants of South America and in the geological relations of the present to the past inhabitants of that continent. These facts seem to me to throw some light on the origin of the species, that mystery of mysteries, as it has called by one of our greatest philosophers. On my return home, it occurred to me in 1837 that something might perhaps be made out of this question by patiently accumulating and reflecting on all sorts of facts. That's my emphasis here, which could possibly have any bearing on it. I can here give only the general conclusions at which I have arrived with a few facts and illustration, but which I hope in most cases will suffice. What a difference to the Newton way of thinking, right? This is not straight edges at all. The world is full of ambiguity and uncertainty. This book is said by some to be the most accessible book of great scientific imagination ever written. And this is the National Water Model. It is a representation of the flow system of the nation. 2.7 million stream reaches covering 3.2 million miles of streams and rivers. This is a simulation done last year for flow for 3 months in 2015. The timestamp is on the bottom right corner. We had a huge flood in Texas right there in the end of May. 50 people were drowned in that flood. And this model became operational and runs now continuously as of 16th of August 2016. It runs by the National Weather Service, runs this in Washington. So there's the weather forecasting and now there's water forecasting attached to weather forecasting. So water has become like weather. And I want to suggest that the National Water Model is a modern form of deduction. It says, given this weather, this is what the hydrology is that we propose that would result from this. In other words, there's a deduction here. So this large-scale computer modeling is a form of knowledge development of deduction. Now, this opportunity occurred because a new National Water Centre was established on the Tuscaloosa campus of the University of Alabama by the National Weather Service and federal agency partners, which has a mission to assess hydrology in a new way at a continental scale for the nation. And that building, really, that's a photo, that's not an artist impression. And you may say, why Tuscaloosa, Alabama? Thank you, Senator Shelby. That's his hometown. What can you say? Yeah. Chairman of the Senate Appropriations Committee, we'll do that for you. And so this centre was established, and it is now a focal point for hydrology for the nation. And in particular, there's 4 water problems to be solved here. Too much water, it's flooding and so on. Not enough water, there's drought. water pollution, there's dirty water, and environmental issues, aquatic ecology and environmental integrity and so on. I'm going to speak about too much water, about flooding, but there is 4 problems to be solved here. Now, the work that has currently being done is at National Weather Service river forecast centres. So this area of the country is forecast by the Northeastern River Forecast Centre, which is located in Boston, and it's the yellow colour that you can see here. There are large river basins here, and there's about 6,600 of them for the country. So I see this as the magnifying glass. This is the big scale view of things. Each of these regions is operated separately, so there's 12 different regional models in the nation, another one in Alaska. That's the current situation before the National Water Model and the National Water Centre got started. Now the intent is to centralise all of this activity in this single centre in Alabama, so that the water forecasting will be done in one centre in one hit for the whole country, and there won't be 12 different regional models operated independently as there have been in the past. Now, at the moment it's running along parallel, so there's actually, they call it the dual track strategy, but eventually there'll just be one system. Like National Hurricane Centre in Miami, National Severe Storms Laboratory in Norman, Oklahoma, National Water Centre in Alabama. Those are the 3 basic centres. This is a group of people that gathered at the National Water Centre in May of 2014. And you can see I'm standing at the back there somewhere. And this is the management of the National Weather Service and its regional centres. And you can see this is a huge building. And somebody asked the question, how many people work in here? And they have space for about 250 people. And they said, well, how many people are going to be here a year from now? And they said, well, maybe 50 people. Actually, 50 people got there 2 years from there. And I thought, well, it was kind of an embarrassed silence. You know, you've got this Taj Mahal, gorgeous, super gorgeous building, and it's not going to have too many people in it. So, but I thought, hey, you could look at that as a problem, or you could look at that as an opportunity. So, hey, we're on a campus. We could bring in students from other parts of the country. So that night, I wrote a letter to an email to the director of the centre, and said, how about we create a new flood data, modelling, forecasting, inundation mapping system for the nation, high spatial resolution, near real time, coast to coast, in 1 year. Just bring in the academic community and crash it out. And I had this idea of reggae music and hackathons and sweaty bodies and people coding all night and that kind of thing. And I put a note at the end of this, if you think I'm too crazy, it's okay, just put it in the garbage can. I'm not going to be personally insulted. That's not what happened. The director put it up on the big screen and said, this is the kind of thing we can do now that we've got a National Water Centre that we couldn't do before, and 2 days later, thumbs up. Okay, we'll go for it. So that's led to an engagement between the academic community and the federal government, and particularly the National Weather Service, for building the National Water Model. And in particular, what happened was called a National Flood Interoperability Experiment. And I've highlighted this word experiment, which was chosen actually at the federal level. Don't ask me, but get me to explain how it got to be this name, but it did. But this is an experiment, and it was an experiment in the sense of an experimental activity, right? We don't know how to do this fully, so we're going to make an experiment just to see what could be done. And what happened is that money passes between the National Weather Service and the academic community through the National Science Foundation, and on the academic side, Quasi, the Consortium of Universities for the Advancement of Hydrologic Science, manages that, and 35 to 40 grad students go down to Alabama for 7 weeks in June and July, for the last 2 years and for this coming year, to work on enhancements of the National Water Model. And this is the distribution of universities that were represented last summer, and the University of Maine is not there. So, okay guys, yes, time for you to step up here. So this year we had 60 applications from 40 universities, and there's plenty of people. Everybody's welcome to come. And if you'd like to engage in this activity as a student and as a faculty member advisor, then this is the way to do it. Now, the goal of the experiment is to close the gap between national flood forecasting and local emergency response. And by this I mean flood emergency response when people have to be rescued when there's big floods occurring. And to demonstrate the forecasting of flood impacts at the stream and street level. In other words, not just for big rivers, but for local streams. And so what that means is that the national level, the National Weather Service and its federal agencies and the National Water Centre are reaching down, and somehow at the local level we've got to reach up at the city and county scale, the state scale, and hold hands here so that this whole system can come together. And I want to explain how that can work. Now, in order to be able to do this, we proposed that the NHD Plus data set should be used, and this is a data set that has taken 20 years to build. So there are 4 national data sets that go into that. The National Elevation Data Set, which is describing land surface topography, the National Hydrography Data Set, which is the Blue Line River Network and water bodies, National Land Cover Data Set, and Watershed Boundary Data Set. Those each took 10 years to build, from like 1995 to 2005. Then it took 10 more years to integrate them, to link the land and water systems of the nation to a series of little catchments. There's 2.7 million of those now. The average area is 3 square kilometres and average length is 2 kilometres, and they're uniquely labelled. So each little stream goes to one, each little catchment goes to one stream and so on for the whole country. And this is one such catchment. This happens to be quite close to my house. This is Bear Creek, actually. It's 5781175. And a sheriff's deputy drove down that street, went over that low water crossing and was washed away. She was killed at that location on September 2014 at 2 o'clock in the morning. 35 years old with 2 sons. Did she have to die? No, I don't think so. I think there's a lot of people are dying in floods that it's unnecessary. I mean, 3,000 people came to her funeral. I mean, when a first responder dies in the line of duty, that's a community level tragedy. And I just use that as an example because I think and the first thing that happened when I saw this happen, I went down there to find out and I said, well, is that catchment in the National Water Model? Sure enough, it is. Obscure place in western Travis County, not even in a city, but an important location. The first version of the National Water Model that we got running was on Stampede. This is at the Texas Advanced Computing Center. Has 500,000 processes operating in parallel. That cooling tank is right outside my office. It puts 60,000 gallons an hour through Stampede in the summertime to keep it cool. And with Stampede, we succeeded in bringing together the flow across the whole country. So we used the weather model, which is called the High Resolution Rapid Refresh Forecast, the HRRR in the top left, to feed a land atmosphere model which calculates the land surface water balance and energy balance called NOAA-MP. It's a standard weather model for that. That creates runoff that gets routed down through the river system. The model is here called RAPID. You can see this for the Mississippi Basin, but later we did this for the whole country, or the whole continental US. And then there's forecasts, and you need those to be, if possible, probabilistic because there's a lot of uncertainty involved. And we demonstrated that this could be done in 10 minutes for the whole country. 10 minutes. Now, I had no clue when I proposed this that it was possible to do that in 10 minutes. One calculation, boom, coast to coast. And we started off with basins and dividing things up into beds and just proved to be, no, forget it. Just do the whole thing. And so what has been demonstrated is that there is just an enormous economy of scale that's involved with supercomputing and with using GIS as a standard data representation to build things on. This WRF Hydro framework stands for Weather Research Framework, and it comes from NCAR, National Centre for Atmospheric Research. That's the basic framework that was used behind this. Now, in doing this, there's 2 different kind of calculations are being done. One of them is how does water move through the landscape horizontally through water bodies and catchments and reservoirs and so on. That's done using catchments and flow lines and water bodies from the National Hydrography Data Set that you see here. And there's also how does the water get there? So there's a land atmosphere calculation going on with weather and precipitation and climate and so on. And the runoff that comes from the squares gets remapped, actually geographically remapped onto the catchments. So runoff from squares becomes runoff on catchments, which then gets routed through the stream system. So there's a vertical piece and there's a horizontal piece in the calculations, and they get geographically connected in the middle. So you could think of this as being a kind of a grid and vector modeling system if you think in spatial analysis terms. What comes out of that is 4 forecasts at all locations. Well, one of them is an analysis which is the best estimate of current conditions. There's a short-range forecast which is on hourly basis for 15 hours ahead, which is updated hourly. The medium-range forecast is on a 3-hour basis for 10 days ahead, which is updated daily. And there's a long-range forecast for 30 days ahead, which is updated daily, and it has 16 ensembles. In other words, there's a different measures of uncertainty there. And I've got a little forecast there for the Penobscot River at Orono, Maine, where just this excitement is in the air here in Orono because you know what's going to happen to the Penobscot River. It's going to go up a lot over the next week. So the current flow is about 18,000 cubic feet per second. Over the next 10 days, it's predicted to go to about 80,000 or 90,000 cubic feet per second. I guess the ice melt, the conditions are starting here. So this is the national water model in Maine. There are 28,859 individual river reaches being forecast by the national water model in Maine. The average length of those is 1 mile, and the total length is about 30,000 miles of rivers and streams. This is what the National Water Model looks like for Penobscot County, and I really applaud the citizens of Maine who've arranged their counties to follow river systems. I mean, very sensible people back then when they drew county boundaries. Here in Penobscot County, there's 3,424 reaches, again about a mile per reach, and there's 8,564 land grid cells covering Penobscot County. And remember, these are being updated every hour. The hydrologic conditions being updated every hour. This is what the Penobscot estuary looks like. So on the left-hand side are the catchments and the flow lines coming down to the estuary. The big blue line is the Penobscot River. You can see that the little catchments go right down to the bay. There's one island there, Sears Island, that I can see is not covered, but the calculations are being done right out onto the edge of the peninsula there, even if there's no river, which is kind of important if you're dealing with estuary processes. And you can see also the land-atmosphere water balance, which is being done on all the cells here that have got a little bit of land in them. So they stop doing it once they get completely over the water. But even if there's a little bit of land, they're doing the calculation. And then if you just look locally here in Orono, here's the two main rivers. We've got the Stillwater River and the Penobscot River, and the land-atmosphere cells. You can see this is the overlay here. It's about, each cell is about the same size as the campus here at the University of Maine. And this is the current forecast for the Stillwater River. So the orange here represents the analysis up to the present. Then there's a forecast which goes out. So for the next 15 hours ahead, as it was about 8 o'clock this morning, you can see there's a little peak that's forecast in the Stillwater River, but the Penobscot River is just forecast to keep on increasing. And then if you go a bit further out, use the medium range forecast, which is 10 days ahead. Both of them go up substantially, but the Stillwater River drops off. I'm sure maybe it's just a smaller river and there's not so much ice to melt in there, but the Penobscot River is due to just keep on going up and up. So currently it's about a little less than 20,000 cubic feet per second, and you can see after 10 days or so it's at 90,000 cubic feet per second. So it's a really interesting, really time of change that's happening here in Maine. Now, what's moving forward happening here? So NOAA has a multi-year strategic science and services plan to be executed at the National Water Model. They call this the Stairway to Heaven. So the first thing was to get the centralised water forecasting thing going, which has been done. Then the next is currently working on flash flood and urban hydrology, which we're currently starting. The next goal after that is coastal integration. So the National Ocean Service and the National Water Service making a single system right around the country for coastal storm surge and flooding. Then there's a drought and fire aspect that deals with groundwater, and finally a piece that deals with water quality. Now the last three steps on that depend on future appropriations from the Congress, so there's some uncertainty there as to whether those will happen or not, or quite in that form, but that's the current plan. Now I want to turn now to the flood problem and to say what we are doing in research now that the National Water Model is running. And that is, we're trying to understand how do we get the water depth and the degree of inundation in a floodway. So you've got the normal channel, you've got the flood fringe, the floodway in the middle. Base flood elevation is something that FEMA worries about for flood insurance purposes, but we're not too concerned about that in what we're doing. And in order to be able to study that, I started to think about what was it that actually is happening. And I realized that we're going from the magnifying glass, or from big basins, which is the top there, to what I've called the microscope, or these little catchments and all the reaches, which is at the bottom. So this is what I mean by magnifying the microscope here. We're going from 400 square miles to 1 square mile. So just imagine, you're looking through a microscope and you're seeing a fuzzy thing, and then you sort of zero in, right? And then some of the things come into view. So this is a very, very microscopic view of the hydrology of the nation. This happens to be on the Blanco River at Wimberley, just upstream of the point where that basin comes out. 2 years ago there was a house. There were 9 people in the house. The house got picked up and smashed against a bridge, and 8 of them were drowned. And again, I don't think those people had to die. I think they just were in the wrong place at the wrong time. Now, how do you go about doing something like that? So if you think about a single network now, atmosphere to the oceans and coast to coast. This is how the Weather Service does inundation mapping now. This is Onion Creek at Highway 183, which is near Austin. And that little green dot is a gauge, stream gauge. It's also a forecasting point. And as the water depth increases, then it spreads out. And this is a very simple geospatial model. You know, I go up by a foot, I spread my water out, I get a depth grid, I get an area. I go up, I spread my water out, I go up, I spread my water out. So what's happening is that the stream is being sliced along its length. And so I thought, we could do that. And after some thought, we evolved this criterion, which we did not invent. This was developed actually originally in Brazil, called the height above nearest drainage. And so this says that flooding occurs when the water depth in the stream is greater than the height that a particular point on the land surface is above the bottom of the stream. So we just called this criterion height above nearest drainage and said, okay, can we calculate that? Oh yeah, yes, let's just calculate that for the country, which we have. So we took the catchments and flow lines from the NHD Plus data set, the digital elevation model. We put those into the Cyber GIS facility at the University of Illinois, this facility called Roger, and with the help of Xiaowen Wang and Yan Lu there, we calculated the blue surface here, which is the height above nearest drainage, for the whole nation. Actually, we did it in 336 units and merged them together. So the brown there is the elevation data, and the blue is the water. So this is, for those of you who do fluid mechanics, this is Z plus Y, you know, when you have Bernoulli's equation. But this is another example. I mean, could anybody have thought that it was possible to analyze the stream geometries of the whole nation in one hit? I mean, no, I didn't see that was possible, but it turned out to be. Now, another thing that the USGS does is that they have rating curves at all the gauging stations. So this curve is built up from gauging measurements, and it relates the water level that's measured to the discharge in the stream. And so this happens at all USGS gauges. And so if you take this concept and say, okay, if I've got my rating curve and if I've got my inundation map, let's just do that at all the stream reaches of the nation in the NHD Plus dataset. And so if you take a stream reach and you say, okay, my water fills up to a certain level, it spreads out, there's a surface area, there's a volume of water, there's a bed area underneath the surface, and if I divide the volume by the length, I get a cross-sectional area. If I divide the bed area by the length, I get a wetted perimeter. If I divide the surface area by the length, I get a top width. And if I divide the area by the wetted perimeter, I get the hydraulic radius. For those in engineering, this is familiar territory. This is what you have to have if you're going to do hydraulic calculations of flow and channels. So it's possible to derive, by geographic calculations, reach averaged values of hydraulic properties for stream channels. Now, traditionally, that's been done by cutting cross-sections. But that's why we've been doing that, because we've been doing it for 50 years. That's why. We don't have to cut cross-sections. We can go this way. We don't have to go that way. And by going this way, we get the inundation map as well as the geometrical properties. And if we have those properties, we can then apply Manning's equation, and we can build a rating curve for all the reaches that don't have gauging stations. And so then we have a forecast that's coming from the National Water Model, and we can infer the flood depth. So we built those curves, synthetic rating curves for the whole nation, for 2.7 million stream reaches. Now, how do we apply this in Texas? Well, this is the Lone Star State of Texas here, which we've been working on digital flood mapping for about 13 or 14 years. Unfortunately, we spent about at least $50 million and perhaps as much as $100 million on this. We only have 120 counties done. Half our state doesn't have any mapping. Now, more than $2 billion has been spent on flood mapping over the nation in the last 13 or 14 years. That's the B word, that's not the M word. And that's the largest civilian mapping program in the world. And why is that? Because there's $6 trillion being insured by the federal government in assets in floodplains. But however, despite that, lots of places don't have flood mapping. We have also collected address points. So who knows what an address point is? Okay, we've got some address pointers. Yeah, so this building has an address point on it. If somebody calls for an emergency vehicle to come to this building, the dispatcher sees a dot and says, go there. So every building everywhere in the country has a dot on it. The counties compile these. This is part of the emergency response system of the nation. So we brought all these data together for Texas. We have about 8.7 million of these points. And then we can say, oh, if we have a particular address point, how high is that above the nearest stream? And that gives you a measure of flood risk, actually. and that the accuracy of that measure depends in part on how resolved is the terrain data that you're working with. So when we started this work long time ago, we had 90-metre elevation models. The Defence Mapping Agency produced them. Then in the 1990s, there was a big revelation. We went to 30 metres. That was the first version of the National Elevation Data Set. Now that's gone to 10 metres, and now LiDAR is surpassing that. A new measurement technique which involves a laser beam being propelled out of an airplane and getting much more accurate information. Now, what we're working on currently is with the National Elevation Data Set 10 metres, but what we would like to migrate to is LiDAR. And if you do that, and we've done that here in South Austin, the colours here represent the height above nearest drainage. So red means less than 10 feet, orange means less than 20 feet, yellow means less than 40 feet, and the greens are higher up. And you can see immediately where the areas are that are at risk. It's not, you don't have to be a rocket scientist to pick that out. And if you say, oh, but we've got detailed engineering mapping that is involved with these kinds of things, are the same kinds of patterns apparent? And they are, actually. So what that says is that empirically derived measures of height above nearest drainage give risk patterns that don't look that different than those that come from detailed engineering modelling. Now, another interesting perspective on this, especially about how to draw maps, is this is Chief Todd Pomeroy. He's the guy that runs the boats for the rescues, the swiftwater rescues in Austin. They have 6 boats, like what you see in this picture. And he was at this location on Bluff Springs Road last fall when there was a severe flood on a creek called Onion Creek. And his chief was calling him saying, how big's the problem you're facing, Todd? And he said, look, I'm getting my guys out on the creek. I haven't got any time to figure that out. But what he does is he puts a rock on the road, actually. And if the water's rising, then the rock gets submerged. If the water's falling, then he sees that. And I saw also that they're also working a lot with their phones. The first responders are texting each other, actually. It's not quite outside the whole official communication system. And if he just, where he put the rock, just sent in a text and said the water is there, okay, there's the height above nearest drainage. Okay, there's your map. There's your risk. Here's how many houses you're dealing with. So in other words, you could be building inundation maps directly derived from the observations made by the first response community. And that turned out to be a really important thing. It's not enough to be able to say, oh, we've got this federal brain in the sky that's telling us all about what's happening, and now I'm going to convert forecast of flow into a forecast of depth. We need observations from the local people who are there and can really see what's going on. We need to bring those two things together. So deduction, experiment, observation. Those 3 things coming together are important here. Now, what's going on now, we've been able to build a cost-effective flood response mapping for our whole state in 1 year, for $600K, frankly. And if this work had been done by the traditional method that's used for FEMA flood mapping, that the minimum cost is $500 a stream mile. That would have been 190,000 miles by $500, which is $95 million for our state, $1.6 billion for the country. There's an enormous economy of scale that's being achieved here. If we can pull off this with GIS, with high performance computing, the economy, the cost economy of being able to give flood resilience to citizens is going to be materially improved. Now, yes, we can perform computational miracles, but are you right? So we're doing integrity checking by comparing with the Corps of Engineers flood models. This one called HECRAS, which stands for River Analysis System, is the traditional method for doing flood mapping. And also comparing the water depths that we're calculating with those that are being measured by the US Geological Survey, the Lower Colorado River Authority, and so on. And all the green dots on the map mean that the calculated water level was within a foot of the measured water level. And the blue and reds are where there's busts. Now, that's not the only check that needs to be made. There's uncertainty in modelling the flow. This month, the National Centre for Atmospheric Research is going to issue a 23-year retrospective run of the National Water Model, which is sort of a reanalysis of what the hydrology of the nation looks like, which will help to quantify the errors in that. Then you've got the error in converting the flow to the depth, the error in converting the depth to the inundation, which you can check with existing mapping, and then the error in converting inundation to impact. How many houses get flooded? How many address points are really flooded? How does that compare with what actually happened? So there's lots of adjustments that are needed to sort of tighten this down, but what I say is that now we have known unknowns. When we started this project, we had unknown unknowns. So, oh my God, it was really stressful. The last 3 years of my life have been the hardest of my professional career. But now we're getting to the point that we like to deal with, right? We know what we don't know. So let me say, is it possible to construct a continental scale version of inundation mapping? And I think that it is. So in other words, if you take the same thing that I was just showing you for Texas, you do it across the country, you take the forecast discharge, you convert that to a depth, the depth to an inundation to an impact, yeah, we can do that for the whole country actually. And this, for the Weather Service, is the holy grail. If they can pull this off, it's going to lead materially to an improvement in public safety, and that's where they want to go. Now, I referred earlier to the 4 water problems to be solved. So this is not just about flooding. This is about drought. This is about water quality. This is about environmental integrity as well. And I want to ask you a question. I want to say there is a national water model. Could there be a Maine water model? So I've been so impressed since I've been in Maine. Water's everywhere, right? You drive along the road, you look, oh, there's more water, there's more. I mean, water's amazing. You've got the coast, you've got the rivers, you've got the water bodies. They're all interacting with one another. You've got ice. I've heard lots today about ice. Water connects environments. Water is a very integrative thing. Groundwater, surface water, people, and so on. And above all, of course, water impacts people. So I want to go back to the 3 ideas about building knowledge that I started off with here. There is a deductive mechanism now that's operating at a microscopic scale across the whole nation, a framework, an integrative framework that has been set up that could be leveraged. I want to suggest that that lends itself to experiments in being varied and looking at what alternatives might mean. We discussed a lot today with Sean about the storage, water storage. There's a lot of discussion about how much water is stored and what impact does that have on stream systems. And storage isn't a big deal in the National Water Model. It's largely dealing with the soil. I think that's kind of a lacking piece in that. And of course, observations are so critical. You can't build a deductive system and imagine that you've got everything right. You've got to temper it with observations all the time. And I want to suggest that geographic information systems are central to being able to bring all this together. There's just not a prayer that this whole process could have occurred unless there was a GIS framework that to be able to take the square cells and map the water onto the catchments, to do the stream system and have all the blue lines and to show all the detail that I showed at the Penobscot estuary, impossible without GIS. So what's happened here is that water has become part of GIS. It used to be that GIS was used, I'm going to build my input for my hydrology model or something like that with a preprocessor. No, this is a different thing. Here the GIS is the information framework and the models are being made to conform to that. That's a new development in the country and it's a critical piece of the scaling of this whole process. And of course it lends itself to how do you do more detail? Well, you put more detail inside of the system that we have now. So let me finish then by saying, I want to say that the National Water Model is transformative for the nation. I mean, this is a once-in-a-generation thing that happened. I've never, I've been 36 years on the faculty of the University of Texas. We've never had anything like this before. And probably I could have been there another 36 years and we might never have had it. It provides an integrated framework for studies of hydrology, hydraulics, water quality, ecological integrity, at the local scale, because you can isolate pieces out and just look at what the external impact is on them, because that's being calculated by the National Water Model. You say, I want to just study this piece, and I don't have to worry about all the rest of it, because I've got some boundary conditions I can draw. I want to suggest that this height above nearest drainage method is an effective way of describing stream channel geometry, and it can be applied at mass scale. You don't have to send out survey crews everywhere and so on. We can use observed terrain data to do that. And finally, I want to suggest it would be fun to build a Maine water model for Maine-specific conditions. This is not Arizona, this is not Florida, it's not Texas. It's a bit heroic to assume that one set of math is going to work for the whole nation. Thank you.
Please, we'd like to. Any questions for David?
Yes.
Ways would the National Water Model be useful for the development of the water model in Maine? Can you base it on that and go from there?
Yeah, what I would do is I would use the same geometrical framework, the 1 kilometre cells, because that's how you can just get the weather driving data directly, and start with the NHD plus, which is 100,000 scale mapping. Now, there is a more high resolution version called 24,000 scale NHD plus, which actually I think has been finished for Maine. So there is a possibility of being able to have catchments within catchments and streams within streams and so on. But I would start with the existing model and densify that, but think about the groundwater and water storage side of this in a more thorough way than has been done up to this point, I think. Yes?
If you think that that the structure here could serve in the same way that NCARs use the atmospheric model for chemistry and the sediment.
Yes. Yes, absolutely. That's the whole story, right? In NCAR they started with the atmospheric model, and then they've got atmospheric chemistry and deposition and all those kinds of things. Absolutely. This is an effort that's in its infancy compared with those, actually. Yes, sure.
Earlier today, you mentioned something about data collection and DOT and your observation of I-95.
Right. So then, now, an obvious question is, you've got now this water model is predicting things at an incredible scale compared with what we've had up to this point. We have 2.7 million reaches being forecast and 7,000 being measured. That's 1 measured for 340 being calculated. So who's going to come to the rescue here and measure lots of things? So I've been beating up on our Department of Transportation, and I said, look guys, why don't you think about just putting a sensor on a bridge? Whenever you build a bridge, hey, you put a water sensor on it. It's like putting the white. And they said, how much does it cost? I told them that what it cost. They said, the white line costs more than that. And so that argument is starting to get some traction, actually. And I've learned something, and that is that our Department of Transportation, the bridge is their thing, right? This is what we do. This is a part of our heritage, you could say. And doing it well or doing it better is something that, they start to get the feel for. And so when you think about Maine, what have you got? Hey, you've got a transect line. A nice transect line, north to south, I-95. Okay, you persuade the DOT to put sensors all along I-95, and you've got a measurement system there that's going to give you a pretty good handle on what flow is coming down to the coast. If you could do it somewhere also on one, you're going to get a system that will measure at the coast as well. And one of the things we've been testing is measurement of the water surface elevation and also of the velocity, so that if the velocity reverses itself, you can sense that. So that's right. DOTs could be a help here. Yes.
What has the destruction and construction of dams done to the construction of the model?
Not much, because it doesn't do a very good job of dams. There's only about 1,200 dams in the whole system, so it's way underpopulated for dams. That's the single largest shortcoming of the existing system, and particularly the big dams are not there, like Boulder Dam and that kind of thing. So there's a long ways to go to get the dams correctly represented, and especially those that are controlled reservoirs. And the uncontrolled ones, you can describe the hydraulic characteristics, and then the water flows over them, which is how the 1,200 are handled now. But no, the dams are not well represented in the existing model. Yes, sir.
Are there any major simplifications that you made in this model for the sake of it being so easy to compute time series continuously? Such as resolution or simpler methods for routing or runoff reduction, anything like that?
When we did the prototype, the land atmosphere calculations were done with 3 kilometre cells, that's 9 square kilometres, and the operational version was produced with 1 kilometre cells, so that went 9 to 1. To be frank, I don't think the computational burden is the limit here. What's been demonstrated is, I think they're only using 600 cores for the current national water model, only 600. 600 is puny compared with 500,000. And we were only using 250, I think, when we did the prototype. So compared to the capacity of existing supercomputer systems, we're not pinging them that hard. I would say that the limits are more how to build and operate robust systems that won't break. The more exotic computational methods are more vulnerable to breaking in circumstances that you just didn't anticipate. So I would say that's more of a risk than the computational burden. I might be wrong. And I would say, let me frame this another way. The computing the weather system is a lot more computationally burdensome than computing the water system. Our system is simpler. It's not as simple as all those Navier-Stokes equations in the atmosphere.
we were to operationalize a main water model, how do you see that rolling out in terms of it being sort of a regional piece of a national model and how that will?
I think the question would be, how can the federal government do a better job of Maine? If you ask that question, just forget about the rest of the country. Well, first you have to build a prototype and show that it will work with the modifications that are necessary for Maine. And then you need to get it rolled into the national system so that it can be operationalised. Now, if an effort is not made to build a Maine water model, what will happen is it'll just go on doing what it's doing now, which is the same as it's doing in Arizona and Texas and so on. So I would suggest, I would see that a Maine water model could be run on a semi-automated basis, like what we did for the National Water Model during the summer of 2015. You'd have to get access to the supercomputing environment, but that's the NSF exceed process. I mean, there's a way of doing that. And then we were asked to just make our jobs high priority, but not exclusive use of cores, because they don't like exclusive use of cores. So it'd have to be like that. You'd have to tolerate some interruption. But other than that, what we did for the prototype was we were getting the real-time weather feeds directly from NCAR and from the National Weather Service, and we were just driving the whole national model in Austin as if it was the real thing. And I don't see any reason why a Maine system couldn't be done similarly. Yes?
Are you able to accommodate variable resolution such that you can use really high-resolution GIS products for the most sensitive areas?
That's a really good question. So this year at our Summer Institute, there's a theme called Hyper-Resolution Simulation, which is designed for that purpose, right? How do you take, just now a severe storm is happening over Maryland or something, how do we just shrink down this whole system just to look at Maryland or Maine, for example, and don't worry about the rest of the nation, and really do a much more thorough job on that. So the thinking about that is that there's actually a separate system, a hyper-resolution system, that's kind of an off-ramp. Right? This is not going off and then coming back, no. The National Water Model just gives off some stuff, and this other thing that's running off, that's kind of on the off-ramp, it's doing its thing. So there's a Professor Fred Ogden from the University of Wyoming, and he's got a model called 80 Hydro, which they're going to run experiments on to see if they can do that this summer in the Summer Institute. Yes?
So what is the interface for the model solutions? Like we were talking about clam diggers, for example, on the coast of Maine.
Okay.
Are you able to access this information?
Yes, indeed. So, well, I mean, hey, I'll do it right now. So, yes, if you do you want to allow Mozilla? Whoops. Firefox is installing your updates. Oh, good for Firefox. Really happy about that. So if you go to National Water Model, NOAA, and it says Office of Water Prediction here. And then now this is the part where you really got to know where to go. It's one of these, only the secret handshake people know. So you go down the bottom here to where it says Mapping Interface. And this is going to bring up a map of the nation. Then you sign away your firstborn child and sign in blood. I understand that we're not responsible for any. And this is a map of the whole country. So if we zoom in here, so where are we? Let's see. Am I going far enough?
Keep going.
Oh, that's Connecticut. Okay, I'm still. Yeah. Oh, sorry about that. Okay. Okay. Yeah, very good. Okay, this is good. So, so let's go here to the Penobscot estuary again, and so, let's come into where we are here. So what I was doing in my little hotel room was I was zooming into this location. Let's see.
A little upstream.
Upstream.
We're at Bangor.
Bangor.
Orno's a little up.
Okay. Orno. Okay.
Almost. There you go.
There we go.
Okay, there you go. So here's our So this is what I was doing this morning. I was clicking on the Penobscot River, and so I should be getting something here. There it goes. So here's the forecast of Penobscot River at Orono. So this is analysis in the short range forecast. This is the medium range forecast, and that's how I got the graphs that I was showing you. Actually, this has changed a little bit. That's interesting. So this forecast this discrepancy wasn't there this morning. So these forecasts are changing kind of all the time. And you see, there is an interesting change. So see how this is now dropping off. So the forecast that I showed you this morning had this thing kind of zooming on out. Right here, it's dropping off a bit. So this is things are being adjusted all the time here. This is not just a static system. And this is the long range forecast. Goes 30 days out, and you can see this going up, and then I guess 30 days out, going into May, you've got the main ice melt has passed, and things are dropping off here. Now there's actually 16 curves here, but you're only seeing one of them. Now if you want to get the data directly, there's a website that you can go to, and that same page that I showed has the link to it, and you get a file for every variable, for every forecast, for every time step, and you have to unscramble those. It takes quite a bit to do that. Yes?
What happens at political boundaries? So in your Texas model, presumably rivers cross state lines. How do you deal with that?
In the National Water Model, they don't care. It's one network, atmosphere to the oceans, coast to coast. It doesn't.
You had a model for Texas alone.
Yeah, so what we did there was we just, we selected, I'll tell you how we did it in GIS, okay? So what I do is I take a political boundary and I select all the features who have their centres in, and then I give the shape that I want to achieve. In this case, Texas. And it select all the reaches that have their centre point in Texas, and I just extract those out. And then I build a representation that is just for those reaches, and I ignore the rest, actually. Yeah, so we just, there's 2.7 million reaches for the country, there's about 100,000 for Texas. We just ignore the other 2.6 million. And the same at the county scale. What I was doing for Penobscot County, I was doing the same there. I was just saying, give me all the reaches that have their centres in Penobscot County. And I excluded all the ones that were in the rest of Maine.
So river crosses Penobscot County boundary, that river is just ignored?
It's being calculated in the National Water Model, but I'm ignoring the result. I'm just picking out the results that come from within the county. Yeah, so the Weather Service is calculating everything, everywhere, all the time. But for my particular purposes, I'm putting on a blanket here, and I'm just focusing on particular areas that are of interest to me and ignoring the rest. Yes?
Ben, do you have any idea of how precise or accurate your measurements are being in the eastern Sierra or the heavy, really heavy snowpack this year?
Peter, I don't know. I haven't examined that question carefully, but the Worf Hydro group at NCAR has. So there's a woman there, Aubrey Duger, and she's doing accuracy measurements for all the river forecast centre areas for the whole country, for different forecast products, and there's an exhaustive assessment going on about that there, but it's really at the professional level that has to be done because you've got to have access to all the data, and so NCAR is doing that. I don't know about the Eastern Sierras, and there are definitely areas that are better and areas that are worse, and some that are not done at all. For example, the South Florida, where they've got all the canal systems around Miami, just don't go there. It's all constructed in a pump system. There's no forecast there. Yes?
So for states like Maine and Texas, which are not like totally, but definitely relatively homogeneous, relative to some other states, like Colorado, how would you go about constructing a model in a state like Colorado? Because at that point, the state boundary matters less than the different topographical zones, I guess, and biomes.
Well, right now there's one uniform model for the whole country. So it's soil, it's vegetation, it's parameterized on a 1 kilometre basis for the whole nation. That's how it's being done. The differences between eastern Colorado, where you're in the rain shadow and you've got very dry conditions and grass and so on, in the mountains in western Colorado are handled by the terrain data and the soil data and the vegetation data that are included, and the land cover data that are included in the parameterization of the model. I mean, to the extent that's possible.
Okay. Well, thank you very much again, David.